Hello, everyone. I'm Liu Pan, the Chief Product Officer at D2S. Today, I'm going to present you my talk at SPIE Advanced Lithography. It's an invited talk. The title is Why the Mask World is Moving to Curvilinear. Hopefully, by end of my talk, you will gain some insight. You have seen so many curvilinear mask talks at SPIE Advanced Lithography this year and last year. You must be wondering why. And I think most of you know the simple straight answer. Though the simple answer is because of process window, because curvilinear IoT can actually significantly improve the process window. And here is a study that we presented together with Micron in 2019 at Bacchus. And we showed that by using curvilinear IoT, we can actually improve the process window by over 100%. As you see in those pictures, at the nominal condition, both OPC and curvilinear IoT get the pattern printed correctly. But if you look at the 60 nanometer defocus and the 60 nanometer defocus with a 93% dose, then you see the OPC print really bad, while IoT with the curvilinear assist features that actually maintain the pattern really well. That's why the process window is much larger. Well, this is not new. It's actually started 20 years ago. So in 2006, at SPIE Advanced Lithography, Dan Abram and myself, we presented the first technical paper from luminescent called fast inverse lithography technology. And you see the pattern we showed that time is actually curvilinear mask patterns. But the curvilinear mask patterns cannot be written by VSB mask writers. Later on, I'm going to explain to you why. That's why the first time I look at this, so, oh, there's no way the photomask industry can accept it. Therefore, we have to Manhattanize those patterns so that the VSB mask writer can write them. That's why we also showed those Manhattanized IoT patterns. The reason the IoT mask patterns tend to be curvilinear, that's actually related to scanner optics. Here is the simple diagram showing how IoT works. So basically, just like OPC, we create a model that can model the scanner forward simulation, right? You start from a mask pattern, you can simulate the wafer pattern. Then we are trying to solve the inverse problem. By giving a wafer target, we iteratively solve the optimization problem so that we end up have an optimized mask that will print the wafer target. So that is IoT. And because the scanner optics is band limited, that means if your frequency is too high, then it won't pass the scanner optics. So if you have the 90-degree corner at the corner, those frequencies are really high, so it cannot pass. Therefore, the pattern you generated tend to be curved, right? If you have a mask pattern as a square, you know you will end up as a disk pattern on wafer because those high frequency will be filtered out. That's why in IoT, when you solve the inverse problem, you still have this band limited optics. So your mask pattern tend to be curvilinear. To make the curvilinear mask used in production, the number one block, as I mentioned before, is kind of like the mask writing. That's because the VSB mask writer is a single beam, variable shaped beam. So you can actually write a rectangle or 45-degree triangle very fast. So it was designed to write Manhattan patterns really, really fast. But if you want to write a curvilinear pattern, then you have to decompose the pattern into many those small shots. Since the write time is proportional to the number of shots, as you see from this chart given by NewFlare, so the write time will be too long and not practical. Fortunately, the photomask industry recognized that challenge. Both MS and NewFlare, they started the multi-beam mask writer development. In multi-beam mask writer, you have this in the first generation 250,000 beams, and they can write at the same time. And for each beam, you can turn it on and off, and also in grayscale. So you can write any kind of pattern, any shaped pattern in a constant write time. So that actually removed the biggest roadblock that prevent curvilinear masks to be used in production. That's why now the confidence on curvilinear masks in the photomask industry is actually very high. You can look at this survey by eBeam initiative. This is a luminary survey, so it means the luminaries in the industry, they look at those questions, then they answer it. And we look at this result for look at both last year, 2023, and also 2022. And you can see the people answered, picked those three answers, meaning either they can handle a limited number of those curvilinear masks, or they have no problem, they can handle as many as they can, those curvilinear masks. Or the third one, they have no problem at all for central masks. You add those together, the percentage is 87%. So it's extremely high. That means the whole industry is very confident on curvilinear masks. Okay, now let's look at a little bit more details. So first, let's look at this full curvilinear IoT can improve process window. So there are numerous studies on this. The first one was done by Luminescent with Samsung. At that time, we generated those curvilinear mask patterns for contact array with a different pitch. And for each pitch, we have the full curvilinear IoT patterns, mask patterns, and then we try to simplify that all the way to just the horizontal and vertical scattering bars. So that's why actually very close to OPC. Then the wafer result was printed. We look at the process window, and you can see for every pitch, the full curvilinear mask pattern always give you the largest depth focus, which makes sense because if you give it the full degree of freedom, then all those S-roughs, they will be placed at the exactly correct location. If you have to constrain it and simplify that to straight, like vertical and the horizontal bars, then some of the S-roughs, they do contribute. Some other part, they actually not really contribute correctly, but they actually made the result here worse, right? That's why the result is actually worse than full curvilinear IoT mask patterns. And this is not just for those old generations, the 65 nanometer generation, but the recent result, this is given by Dr. Ezekiel Russell from Micron, and he showed for this three contact by using full curvilinear IoT, they can actually improve the depth focus by 85%, which is similar to the one we saw on the real wafer. So because IoT full chip, because IoT can give you those benefits, that's why now IoT has already been used in production, but they only used in hotspot mode. The reason is there is another roadblock, is a full chip IoT itself, how to compute the full chip IoT. And one is a runtime. And the runtime can be handled by using GPU acceleration. But there is another issue. Only when you deal with a full chip LT, you recognize that that's a big issue. That's called stitching. OPC, basically, when OPC deal with a full chip, it split the full chip into those small partitions, and it calculate the solution from the beginning to the end. It also has a halos, but you basically calculate the solution from the very beginning to the end, then you put them together. That works for OPC, but for IoT, you see the problem is from this left partition, it generated those sroughs, but from the right partition, it doesn't have that srough. So when you put them together, then you have this big problem. And this is called a stitching problem. The way to solve it, you have to take this whole region close to the border, you recalculate the LT solution. But the problem is you create the new partition boundaries, right? So not only this will increase your runtime by pretty much a 2x, but also you have the new problem, so the problem never end. So that's a big headache. And that problem, this stitching issue, was solved by D2S. We came up with a new idea. We call it a gigantic CPU-GPU pairs. The idea is you put the entire design into the memory, and you have all those GPUs, they iterate at the same time. So in each iteration, we actually solve the entire design, then we move to the next iteration. By doing so, we don't have such a stitching problem at all. So you look at this blue contour, you see all those sroughs, when they cross those partition boundaries, they are actually continuous. So this totally solved the computing issues for full chip curvilinear IoT. Then you must ask this question. So if the corner is filtered out by scanner optics, as I pointed out at the beginning, so why do we care? Why just live with it? Well, it turned out there's some benefit by changing the pattern from Manhattan to curvilinear. So first one is related to mask rules. So it actually can enable smaller pitches. So here is a simple example. Think about a contact array. You can actually use a square shape on the mask, or you can use a disc shape on the mask. But how small you can pack, or how tight you can pack those contact array, well, it's actually limited by these mask rules, basically the minimum corner-to-corner rules. Without changing this corner-to-corner rule, if we just change the shape from square to disc, then the pitch can be actually reduced by 14%. So that's actually very significant. Not only that, if you do curvilinear, then the mask rules becomes much simpler. There are only minimum curvature, minimum CD, space, and a minimum area. Here I give you an example. Just imagine this is an intuitive way to think about the problem. If you have a certain sized ball, and this ball, the diameter can be your minimum CD. So if you roll the ball along the contour inside your pattern, if it doesn't stuck, that means it satisfies the minimum CD rule. If it stuck somewhere like here, that means that this place violate the minimum CD rule. And similarly, you can roll the ball outside of the pattern. If it is stuck, that means it violate the minimum space rule. And you can change the size for minimum area, and you can have another ball has a minimum curvature. You can roll them around. Of course, the real algorithm is not like this, but such similar algorithm we can implement it using pixel computing. It's actually really fast as well. Not only curvilinear mask patterns give you some benefit, But actually, if you don't do curvilinear mask patterns, if you stuck with Manhattanized curvilinear, like a Manhattanized curve patterns, then it actually has problems. A lot of people don't recognize or don't realize that. There are two big problems. One, I already talked about this shot count and the right time, because once you Manhattanize with so many jogs, then your shot on VSB mask writer will be extremely long, right? But there's another problem. That's called the dose margin. Basically, the variation on mask writing to write those 90-degree corners will be much higher than writing just the smooth patterns. So we call that dose margin. Well, just a very similar to lithography. In lithography, we talk about process window. We know process window has two variables. One is a dose, the other one is a focus. For mask writing, there is also a process window, but because it's a eBeam has an infinitely long depth focus, so we don't really care. We don't have to care about the focus, but we really care the dose. The dose can actually change. So in lithography, we call that dose latitude. In mask making, we call that dose margin. It's a similar concept. Basically, it's when you change the dose to a certain amount, you want to look at the pattern change, right? If the pattern change is large, that means it's a bad dose margin. So here we can calculate the dose margin and use a pseudo color to represent the dose margin. The red is a bad dose margin. The green is a good dose margin. And you can clearly see for those 90-degree corners, the dose margin is actually worse than those smooth regions. And this study was also done by Dr. Perman a couple of years ago. It will take a while to kind of like explain his chart, but basically he showed if you have a disk pattern, then the dose margin on any direction, they are good and they are the same. But if you look at the square shape, so on the straight edge, the dose margin is good, but on the 90-degree corner, the dose margin is actually really bad and not acceptable. Not only just the dose margin is bad, but it turned out MEEF is actually also worse. So here is another study done by Abhishek from D2S. He looked at this angled line I showed you before, and either you do that with a straight angle line, or you do with these staircases. Then he compared the MEEF. It turned out for both the middle edge and also for the land, the MEEF on this staircase Manhattan pattern, they are actually worse than the smooth pattern. And the smooth curvilinear pattern, they actually improved the dose, improved the MEEF by 28%, which is very significant. You must ask why. Here I give you some intuition. So just imagine you have a square and you have a disk. If you change the shape by 1, then you see for the square shape at the corner, it's actually changed to 1.4. Well, on the disk pattern, no matter where, the change are always just 1. That's kind of the reason why the MEEF is actually worse for Manhattan 90-degree corners. Okay, now you have those. We have those theory. We should look at on the real mask and look at the variations. Compare the variation on the mask between Manhattan pattern and the curvilinear pattern. So we did this study at Micron. So we look at the Manhattan masks and the curvilinear masks. For each of those, we have those patterns. We placed it many copies, and for each contact, we can align those all together, right? Once we aligned, we extract the contour, we align all those contours, then we can look at this variation band. So basically, it's just very similar to the PV band, right? This would be the mask variation band. And we measured every 4 nanometer, right? Then we can look at the statistics. So here we look at the contact array. We have 4 locations. In the contact array, we look at the center of the contact array, the left edge, the corner, and the bottom. So you can imagine at the center, they are just the contact array, the main patterns, but on the edge, we also have the SRAFs, and the corner has more SRAFs, right? And those are the 4 locations. Then we have 6 copies, same pattern, 6 copies on the mask. And for each location, we measured like hundreds of hundreds of contact. And for each contact, every 4 nanometer, we have a measurement. So now we have this bandwidth. We plot the bandwidth. We compare those two. The blue is a D2S curvilinear. The orange is a Manhattan pattern. And clearly you see there are 2 observations. One is the curvilinear pattern, they actually shifted to the left, meaning they are closer to 0. So meaning their bandwidth is actually smaller or tighter. Second, you look at their distribution is also narrower. That means their bandwidths are kind of like a more constants, right? So the variation is also the bandwidth variation, the bandwidth variation is also smaller. Okay, now we plot all of those. So we plot the mean, standard deviation, and max. And here as I mentioned, we look at the 4 locations, the center, left, bottom, and the corner. And each of them, this is that variation bandwidth. So you look at from the Manhattan, which is orange, to blue, that's a D2S curvilinear. So you see the mean, standard duration, and max, they all dropped, right? And they dropped for all of the locations. On the right axis, we look at this improvement, or the variation reduction, and we plot it. This is this green dot. And you can see on average, for mean, standard duration, and max, we all improved pretty much like 20%, right? So that's very significant. Remember, this is the same mask written by the same multi-beam mask writer, just the pattern. One is a curvilinear pattern, the other one is a Manhattan pattern, but the curvilinear pattern mask has a 20% smaller variation than Manhattan pattern. That is very significant because with a MEEF, this will translate to the smaller variation on wafer as well. All right, so now we know with a multi-beam mask writer, definitely it solved the problem to write those curvilinear masks, and also you have a smaller variations. But what about VSB mask writer? Is there a hope we can actually still do curvilinear mask, but with a reduced variation? The answer is yes. The trick is we have to reduce the number of corners, right? If we have a few number of shots, that means we have a few number of corners, then that will reduce the mask variation. And we can actually use this new technology we call mask wafer co-optimization. The trick is we are going to do double simulations, the mask simulation and then the wafer simulation. And based on the wafer result, we will iteratively move those shots. And you see here, we have the overlapping shot on the assist feature that will improve the dose margin, make the slope steeper, and also can help to end up with these curved features. By doing so, we actually have a less number of shot than OPC. That means the write time is actually faster than OPC. It turned out we can actually write this within just the full curvilinear mask within 12 hours on VSP mask writer. And here are the mask. So you look at it on the right. This is a MWCO curvilinear mask. See, the main feature, we are not using overlapping shot, so they are full curvilinear. Assist features, we are using overlapping shot, so that dramatically reduce the number of shot. And we use a bigger shot that actually helps the dose margin. So with that, we look at on the wafer and we see MWCO double the process window than OPC, and also the write time is actually faster than OPC. That's very, very significant. So in this plot, so green region and the yellow region, they are kind of like within the process window. The red region, they're outside the process window. You can see the valid process window on MWCO is more than doubled than OPC. All right, there's still more work to do, but all those can be done. You look at this conference, there are many talks talking about multi-gun format, for example. So that will help reduce the file size on curvilinear patterns. And also by using the multi-gun format, OPC can become a curved OPC. Instead of moving the segment, they can move those control point, so they can do curved OPC as well. So I would say with this, you look at our world. Our world is actually curvilinear. All those Manhattan are created by our human. Then we see the trend on the mask world. We are also moving to curvilinear. I hope this gave you some insight. And thank you very much for your attention.